Okay, so the last talk today is by Kenneth Blakey from MIT, and he will talk about bounding Lagrangian intersection using Floer homotopy theory.
Yeah, so thank you for the introduction. And yeah, thank you to the organizers for the invitation. So I want to talk about, I guess, a recent preprint that it applies Floer homotopy theory to a rather classical problem of just bounding Lagrangian intersections. Yeah. So first, I want to talk about what's known just using Floer cohomology, for instance. So M will be some symplectic manifold, and L0 and L1 will be two Lagrangian submanifolds. And a classical question is how many points does L0 intersect L1 in? And the answer or partial results to this really depend on what the underlying geometry satisfies. So one assumption is that we can take M to be closed, or Louisville. We can take L0 and L1 to be Hamiltonian isotopic via compactly supported Hamiltonian isotopy in the Louisville case. And so either Li is connected, closed, and relatively exact. So there are no every disk with boundary on Li has zero symplectic area. So in this under these assumptions, the Arnold conjecture states that the number of intersections at L0 and L1 is at least the number of critical points, the minimal number of critical points of any smooth function on either L0 or L1. And if the Arnold conjecture is true, then this bound is going to be sure. So I guess the first result by Floer in 1988 in the transverse case, so suppose A1 and that L0 intersects L1 transversely, then in fact the number of intersection points is bounded below by the ranks of the Z-mod 2 homology, the sum of the ranks of the Z-mod 2, singular homology of the Lagrangians. And so we can ask the question if, or we can ask whether or not we'd like to ditch the transversality hypotheses. Let R be a commutative ring, and let C sub R of X denote the R cup length of a space. So this is going to be the longest chain of cup products that exist on the space X. And so a theorem due independently to Hofer 1988 and Floer 1989 is suppose this assumption A1, then the number of intersection points of L0 and L1 is at least the Z-mod 2 cup length of the Lagrangians, which will be the same. So because they're Hamiltonian isotopy. And in fact, recent work of Hershey-Percelli generalizes this using Floer homotopy theory. So again, under this Hamiltonian isotopic assumption. So now the script R will denote a ring spectrum, which represents some multiplicative cohomology theory. So we can define a cup length in this cohomology theory. And if we suppose this assumption, this Hamiltonian isotopic, and we assume some R orientability hypotheses, meaning that the moduli spaces with Floer trajectories that arise, they're oriented in some sense with respect to this ring spectrum. Then in fact, the number of intersection points of L0 and L1 is at least this R cup length of the Lagrangians. And so, in fact, Hershey-Percelli showed that this is a strictly stronger bound than the non-Floer homotopy bounds by exhibiting two examples of SP2 and SP3, the zero sections in the cotension bundle. They show that there is a ring spectrum that has a better cup length bound than the integral cup length. Okay, so now the real motivation for what I was interested in is so what if we want to get rid of the Hamiltonian isotopic hypothesis? What if we want L0 and L1 to not be Hamiltonian isotopic? So one thing that can be shown is just before getting to Floer homotopy is one can consider the quantum cap product action on Lagrangian Floer cohomology, which makes Lagrangian Floer cohomology a module over the singular cohomology ring of either Lagrangian. And it's given by a count of strips with an incidence relation on gradient flow lines of a Morse function on one of the Lagrangians. This will give you some module structure on Lagrangian Floer cohomology. And one can show a quantum cap length estimate as follows. So suppose some assumption A2, which I didn't specify, but it really just says that the Lagrangians have a definable Z-mod 2 Floer cohomology. And suppose there exist alpha 1 through alpha k that are singular cohomology classes on L sub I, together with a Lagrangian Floer cohomology class, such that the quantum cap length or the quantum product is not zero. Then, in fact, one can show that any compactly supported Hamiltonian deformation of L0 and L1 has to intersect in at least k points of distinct action. So recall that there's this action functional on the path space between the two Lagrangians, and we can associate an action to the intersection points. And so not only do we get k intersection points, but they also have to be of distinct. And now the question is, can we do better than this using Floer Homotopy? And so I wrote this big assumption, this big technical assumption, that'll make it to where the Floer Homotopy type exists. And I guess really the thing to say is so we're going to work in the exact setting. So M is some Liouville manifold, and the Lagrangians are either closed exact Lagrangians or they're cylindrical at infinity. So they're modeled on some product with the Lagrangian out at infinity. And we need this notion of this framed brain structure. And I guess quickly, just what to say it is, it's a assumption on the tangent bundles of the manifold and the Lagrangians themselves. So stably, the tangent bundle of M, if I sum it with some trivial complex bundle, then I want it to be the complexification of a totally real subbundle. And my condition on the Lagrangians is that I want their tangent spaces, after stabilizing by some real trivial bundle, I want them to be homotopic to this totally real subbundle lambda. So in some sense, I want the tangent spaces. I can deform them to some kind of standard totally real distribution, perhaps after stabilizing. And in particular, I should say that the homotopy of the tangent bundles of the Lagrangians is a part of this data. So it also depends on the choice of the homotopy. And so, yeah, a theorem, I guess, really written by Cohen, Smith, and Siegel, but the details were carried out in Tim Large's thesis in 2021, is supposing this assumption, then the Floer homotopy type F lambda L0 L1 exists, i.e. there's a spectrum whose cohomology or homology is the Lagrangian Floer cohomology or homology. And I guess I should point out, I said the Floer homotopy type, but again, this will depend on the choice of lambda itself. So there could be, in some sense, a priori, there could be many spectra who underlie the Lagrangian Floer cohomology, but that are different spectra if we choose different choices of brain structures. But yeah, so let's get back to intersection. It's not my pointer. There we go. So let's get back to intersections. Let's just suppose for fun at first that our two Lagrangians, satisfying these assumptions, that they just intersect in a single, possibly degenerate point, x. And so here's some little cartoon of what that could maybe look like. And if I zoom in really close to the single intersection point, I can write L1 locally as some graph of an exact one form modeled on the cotangent bundle of L0, like really close to this intersection. And this smooth function denoted f it'll be a smooth function in Rn, and it'll have a single possibly degenerate critical point corresponding to the single intersection. Okay, and if we do a little local deformation to make L0 and L1 intersect transversely, we'll introduce, we'll perturb f to be a Morse function, and we'll introduce some more intersection points. But a theorem of Floer in 1989 says that the Lagrangian Floer cohomology of L0 and L1 in this case is just given by the Morse homology or the Morse cohomology of f, maybe up to a shift in the grading. And I wrote this in green. This is just symbolizing the fact that these are really defined after we take these perturbations. But I just defined this notation in the degenerate case to be the ones after we take some small perturbation. So in fact, the one thing we can do is we can upgrade this to a statement about Floer homotopy theory. So one of the first propositions is that in fact the Floer homotopy type, perhaps after a shift, is actually given by the Morse homotopy type, where this is again some spectrum whose homology or cohomology underlies the Morse homology or cohomology. Right. And I guess the last thing to say in this case, where we're just intersecting the single point, where we're intersecting the single point, is that this Morse cohomology of f is actually given by the reduced cohomology of a space. It computes the reduced cohomology of a space. It's known as the Conley index of f. So in the closed case, the Conley index would just be given by the base manifold itself, disjoint union point. But this Conley index gives you a way of computing, making sense of more cohomology, say on like an open manifold with some conditions. And again, we can upgrade this to homotopy theory. And I say this is essentially a folklore result because in the closed case, this has been shown many times, the Cohen-Siegel framework, or I would say Bloomberg, or things like this. But you can also do it for Conley index theory. So the Morse homotopy type of this function f will actually be equivalent to the suspension spectrum of this Conley index. And so now, this is all to say that the Floer homotopy type of L0 and L1 intersecting in the single point is actually just up to a shift. It's the stable homotopy type of the Conley index. It's a function that locally models L1. And what's the reason for doing all of this? So the stable homotopy type of the Conley index of a smooth function on Rn with a single critical point is actually quite constrained. So in fact, a theorem by Pears in 1994 and its thesis says that in this situation where you have the single possibly degenerate critical point, the Conley index of f is either S0 or it's something called a coh space. So I wrote this definition of a coh space. It's just some space with a homotopy coproduct. But this actually gives some restrictions on the homology and the cohomology of the space itself. And the reason that I wanted to bring Floer homotopy theory into the picture is because I wanted to use Steenrod squares on the Floer homotopy type to say things. So if we investigate the Steenrod squares on this Conley index of f, where we have the single possibly degenerate critical point, we can actually show that the J of Steenrod square vanishes if J is at least n-1/2, where n is the dimension of the Lagrangian. And so from classical algebraic topology, some of the Steenrod squares have to vanish, but the fact that this Conley index is a coh space actually forces more Steenrod squares. So one way to interpret this in our situation is that if the Floer homotopy type of L0 and L1 had a non-zero Steenrod square where J was bigger than or equal to n-1/2, then in fact L0 has to intersect L1 in at least 2 points of pairwise distinct, given by this local equivalence of the Floer homotopy type. Because if they only intersected 1 point, we would just violate this. Okay, so now we can just generalize by filtering the Floer homotopy type by action. So I wrote the statement of the theorem, and below it a little cartoon. So I guess under this assumption A3, suppose that L0 and L1 intersects in chunks of points, possibly degenerate, that are of a fixed action kappa 1 and then kappa 2 all the way up to kappa k. So maybe these are the first 3 points that we intersect in, all of action kappa 1, all the way up to this chunk of points where we intersect in action kappa k. Okay. Then there exist integers and these cofiber sequences of the Floer homotopy type, where the first 2 terms indicate that we're computing the Floer homotopy type only with the intersection points of action at least kappa j. And then the cofiber of this map would be the Floer homotopy type with respect to intersection points of exactly action. And by our previous discussion, this is just given by some wedge sums of maybe shifts of these Conley indices, these functions on Rn that have exactly 1 possibly degenerate critical at the origin. And so I guess one simple corollary of this is that if we take cohomology of this cofiber sequence, we'll get some long exact sequence cohomology. And so in fact, one could prove that long exact sequence without doing any Floer homotopy theory. You just repeat everything I just said, maybe at the chain level. But the reason that the Floer homotopy theory statement is desirable is because when we take cohomology of this cofiber sequence, it'll be compatible with the Steenrod squares. And so the main motivation for proving this is this second theorem. So again, I wrote a lot of things, but I guess the main takeaway is the fact that, suppose these assumptions, and suppose you have sufficiently many integers, integers of sufficiently high degree, is n-1/2, and you had Floer cohomology classes such that you had chains of Steenrod squares that were not vanishing. And under it, there has to be a little degree condition. Maybe I won't say too much about that, but really the point is that you have this non-zero chain of Steenrod. Then any compactly supported Hamiltonian deformation of L0, L1 intersects in at least the number of Floer cohomology classes you have plus the length of each chain of Steenrod squares. So in fact, you get lots more intersection points by considering this Steenrod. Also, just a quick note. So there's this degree condition on how big the Steenrod square has to be. In fact, sometimes you can use Steenrod squares with smaller degree. For instance, when n is equal to 14, the Steenrod square only has to be as big as degree 2. It doesn't have to be degree 2, this theorem would say. And this comes down to the fact that in the proof of this theorem, if you're a bit more clever with like the atoms relations or the properties of the Steenrod squares, maybe you can massage the formulas to get better estimates. So in dimension 14, I could do that. I could massage it a little bit to get a better estimate. And so now the big question, is all of this worth it? Does this bound do better than previous results? So in fact, yes. So we can construct an example, M L0 L1 in this lambda, where the dimension of M is 14, such that the two Lagrangians are not Hamiltonian isotopic. So the classical results don't apply, neither does the generalization for Schiff-Scaling. All the quantum cap products vanish. So this quantum cap length estimate doesn't apply. And the Floer Homotopy type is this suspension spectra of wedges of CP2s with each component shifted by this +8. And this is the reason for this is so that we satisfy this degree condition. And so like an investigation with just the Floer cohomology shows that any compactly supported Hamiltonian deformation intersects in at least J points. This will follow from the fact that given these shifts, you just have sufficiently many non-zero Lagrangian Floer cohomology classes. So just by pure degree consideration, they have to intersect in at least J points. But the beauty is that by considering Steenrod squares, you can improve this bound to 2J. So every intersection point that you could detect by the degree, it actually has to have another intersection point corresponding to the fact that CP2 has a non-zero skew2. And I guess just a word on the construction of how you would cook up such an example. So it's really just this. So classically, there's this embedding of CP2 into R7, and then we can put it inside of S7. We want our Lagrangians to be closed. And now we can plumb together two cotangent bundles of S7 along J disjoint copies of CP2. And the result will be a symplectic 14 manifold with two Lagrangians, they're diffeomorphic to S7. They intersect cleanly in J disjoint copies of CP2. So here's a little cartoon of this. And then the last part is to define some frame brane structure lambda. And the way to do this is that there are two standard, quote unquote, polarizations, R polarization. So this decomposition to a totally real, decomposition of the tangent bundle of the cotangent bundle of S7 into two complexifications of a totally real subbundle. One can take the horizontal bundle or the vertical bundle with respect to some connection on S. And so if we take these two and we glue them together when we plumb, then we would get a Floer Homotopy type that is just the wedge sum over CP2s. We just did the naive gluing. And so the way to get this degree condition is that these plumbings give you some non-trivial loops in pi1 of this symplectic manifold. And so what one has to do is they have to stabilize this frame brane structure by some trivial line bundles and then rotate them along the loops to get these degree shifts. So this will just shift the degree of the generator of the Lagrangian Floer cohomology classes, and then this has to shift the Floer homotopy. And like I said, this is also that this degree condition in the theorem about Steenrod squares is satisfied because you need the degree of the chain of Steenrod squares, and then the next Lagrangian Floer cohomology class to be sufficiently large to make sure they don't have to come from the same degenerate intersection points. You just have to let them be sufficient. Great. And that's all I wanted to say. So thank you for listening.
Thank you very much. Are there any questions or comments or? No?
Do you have a generalization of the main theorem to other cohomology theories, or the Steenrod square condition to other cohomology theories?
Sorry, it's a bit hard to hear. Could you repeat the question?
Sorry, I'll chat. Is there a version of your Steenrod square found in other cohomology theories?
With other like cohomology operations?
Yeah.
Yeah.
Or or some other exotic place.
I see. I would say that I mean, this would go back to having to bound these. So okay, so my guess is that there should be, but this would have to come from constraining these cohomology operations on the Conley index of these functions with these single degenerate critical points at the origin. And so in fact, what's the thing to say? And in fact, I think there should be, because the way one proves that these Steenrod squares of sufficiently large degree on this Conley index vanish is by using some duality result about the Conley index of f and the Conley index of minus f. And there's this paper that relates generalized cohomology operations on a space and then the Spaniard-Whitehead rule of that space. So Tome carried this out for Steenrod squares. And, I can't remember the reference, but I think it's done for all stable cohomology operations. So I think there's probably some combinatorics to do there that one could get some bound.
Cool. Thanks.
Are there more questions? So I have some questions. First, could you give the reference for the paper who says that if you have a single critical point, then the Conley index is H co-H space? I couldn't find. I couldn't actually read.
Claude, just to make a remark.
Yes.
It's a result of the fact that any space of Lustenich-Schnirelmann category 1, it's a co-H space. And in fact, I have a paper about this a bit later than the reference that Kenny gave there, but also the relation between function f and minus f and the Spaniard-Whitehead duality, I think, appears in this paper around 2000.
But could I get the reference of the other paper? I mean, your paper I know I can find, but the other one
I don't know for sure myself, actually.
I couldn't find. I mean, maybe I got the spelling wrong of the name, or I don't know, but I couldn't find. So I don't know if you can share the reference, or if you can email the reference at some point.
Yeah, so I can put it in the chat.
You have it here.
Yeah. So I just put it in the chat. Yeah.
Okay, great. And my other question is, so a priori, if you have Steenrod operations, you don't need the full homotopy type. You just need the cohomology. So is it in the proof? Is it in the proof that you use the homotopy type, or could you just do everything with the mod p cohomology? That was not completely clear to me.
So I guess the thing to say is that so one would have to give a chain level description of the Steenrod squares on the Floer cohomology, and then would have to show that it's I guess invariant under Hamiltonian deformations. And so I think even giving So I guess that's really the main issue. And so when you have the Floer homotopy type floating in the background, you just have these Steenrod squares defined a priori.
Okay. And could you use other things like massive products, for example, to find more critical points?
I haven't thought about that one, so I'm not too
like
sure.
In your paper, Claude, right? You have a paper about that.
Yes.
In the classical case, I mean.
In the classical case, yes.
Exactly.
Yeah. Okay, sorry, I got. Okay, more questions? Sorry, I have a problem with my screen. Okay, if not, I think we should thank all the speakers.